All right, so we're going to pick up with class today. I'll show you a little bit of where we left off and where we're going today, and then a little bit for tomorrow. I will be back tomorrow. So if you look in our Google Classroom, this video is going to be recorded there, so I'll post that for you guys. But we are in week 2, obviously. Yesterday, we actually finished up this graphing speed and slope assignment. So sometimes this takes a minute to load, so I have it over here. This is what it looked like if you were in class on Monday, October 5th. We completed this. If you did not, go back and do this first. It's going to be helpful for the assignment that we're doing today. But a lot of slope formula, obviously, we're kind of comparing that to speed and how we can represent speed in both or through both a formula as well as a graph. So yeah, work on that if you did not get that done. I'm assuming most of you did. I graded those and have returned them into your folders. Where we're going today is this assignment, acceleration and average speed. We'll save this slideshow for tomorrow, actually. I may move that, but we're going to be working on an assignment that looks very similar to what we did today, except for we have a new equation. So finally, our second, or formula, I should say, we're going to be working on today, doing a little bit of graphing with that as well. You guys will also need to have your little student knowledge note sheet that we started on yesterday. We'll be adding some of the acceleration information and a little bit more to the graphing section. So let's go ahead and jump in here, and I'll kind of do this in a couple little parts. So you can feel free to pause this video as much as you want, or watch it all at once and then try to do the worksheet. So kind of a new topic today. We've mentioned the term acceleration a little bit here and there. It's got some things in common with speed. Our formula looks pretty similar. So if you remember, what we had been up to was using our speed formula, which was speed equals change in distance divided by change in time. So you can see with our acceleration formula here, it's 3 variables. A is equal to change in velocity or change in speed divided by change in time. So we're still dividing by delta t. We still have 1 variable over here and then like 2 that are being divided. So very similar setup. We're just not so much going to do this one today. We will continue with it throughout the term, just not quite as much. So we've got a little bit more information. Our 3 variables, A stands for acceleration, V is velocity, or S is speed, and then T is time. And then we have a reminder down here of like, what is delta? It means change in velocity, change in times, change in speed, change in distance. And you're always going to do the second number minus the first number. So that's what, like, specifically for this one is what we've mostly done. Delta T is time number 2 minus time number 1. Or yesterday we did delta D, which was distance number 2 minus distance number 1. So you're going to see many examples of this where you're going to have to do quite a bit of work with the delta. Okay, so here's a little definition of acceleration. It's how fast you change speed. So a key phrase here is for sure change speed, or how much the speed changed in a certain amount of time. So we are going to be looking at examples where 2 speeds are given, and we're going to compare those based on the amount of time that change happened to be able to figure out our velocity. And then over here, they say A is most accurately represented as change in speed divided by change in time, not just speed divided by time, because if a car was traveling at 60 meters per second for 20 seconds, speed would be 60, but change in speed would be 0. So we need to know the change in speed. We need to know the starting speed and the ending speed. Usually those are given as 2 numbers, like it'll literally tell you the starting speed and then the ending speed. Other times it's going to use words like came to a stop or was at rest, often things that will represent the number 0. So I know we talked about that last week. We're coming back to that today too. So we've got a couple examples here. We have one example where we are going to get a positive answer. And it says calculate acceleration. And then a second example down here, it says calculate deceleration. Acceleration is usually a positive answer. Deceleration is a negative answer. The weird thing with that is you also can just call it acceleration. Sometimes it's called positive acceleration or negative acceleration. So the word deceleration, you may or may not see depending on, what textbook or video or a specific assignment that you're doing. So they've given us our kind of like story problem, word problem right here. And they tell us that a plane starts at rest and ends up going 200 meters per second in 10 seconds. And they want us to calculate the acceleration. So if you remember our little 5-step process that we did last week, we're going to read through the story problem first of all and figure out what variables do I already know, what do I not know. Down here, they already said A equals question mark because we don't know acceleration. They're asking us to calculate acceleration. The amount of time, 10 seconds. Usually that one's pretty easy. And then here's kind of our new thing, our S1 and our S2. It says a plane starts at rest. And this is what I just mentioned a second ago. That means 0 is the starting speed. It starts at rest. A plane is sitting there, maybe being boarded by its passengers. It's not moving yet. There is no speed. So our speed number 1 is going to be 0. Our speed number 2 is where it says it ends up going 200 meters per second. So that's where they got these numbers. In order to calculate acceleration, I have to know change in speed. So we did ending speed, 200, minus beginning speed of 0 to give us our answer of 200. We know that this is the formula that we're going to use. And so they said A, acceleration, and I'm going to rewrite it more vertically, equals 200 meters per second. That's our delta S, divided by 10 seconds. That's our delta T. And you can see, obviously, they have the answer here for us on this one. So this is just an example. You would get 20. And then just like with meters per second, when we were solving our speed formulas, and we saw this example last week too, meters per second squared comes from the division of these units happening. Okay, so that's the most common acceleration example, I would say, but you also can get a negative answer. So let's check out this deceleration example. And this time they're talking about a race car. It starts at a speed of 400 meters per second. That's the starting speed, or the S1, and then stops. That's our S2. So that's the tricky thing. You have to know that that's a 0. If something comes to a stop or stops, then that number is 0. And that's the ending speed, so it's S2. And then they tell us the time, 20 seconds, and our acceleration is unknown. So this right here is super important. When we find delta S, you have to remember to do this correctly. Speed 2 minus speed 1, which is 0 minus 400, not 400 minus 0, because you're doing ending speed minus beginning speed. So we've got this little negative symbol right here. And it's going to ultimately give us a negative answer, which is correctly, that's what we want. So still same step over here. I now have negative 400 as my change in speed, and I'm going to divide that by 20 seconds. Was that right? Yeah, 20 seconds. In order to get a negative answer, negative 20 meters per second squared. You still do all the, math the same. You're still plugging it in the same spots, the unit and everything. You really just have to make sure you do ending speed minus beginning speed. Okay, so let's look at a couple more like vocabulary type things. We've actually already done average speed. So this box in pink is really kind of what we were doing the last couple days, but they're telling us that average speed is equal to total distance traveled divided by total time traveled. And here is another data table that we saw the last couple days. So they give us an example of a person who has done a few different legs of walking throughout the day. So the person walks a distance of 4 miles in 2 hours. So they put that information right here. And then they stop for an hour for lunch. They went a distance of 0, but time still passed. So we still got to include that hour. And then after lunch, they incredibly walked 8 miles in 3 hours. So we're just figuring out the total distance, 12 miles, 4 plus 0 plus 8. The total amount of time, 6 hours, because again, we want to make sure we include this 1 hour right here. The 2 and the 3 make sense. Sometimes people forget the 1, so that's kind of the whole point of this. And then you're doing the same thing that we've done for speed, where we're doing the total distance divided by the total time. So 12 miles per 6 hours. Oh, it looks like I forgot there was a typo right here. It says seconds, it's supposed to say hours, in order to give us an average speed of 2 miles per hour. So you'll be using one like this on the back, where you'll just be doing speed instead of acceleration. And then finally, we learned this in one of our videos last week. Speed is a scalar quantity and velocity is a vector quantity. I told you guys that it was just lucky that speed and scalar both start with S and velocity and vector both start with V. So that's kind of an easy way to remember it. You still have to know what those things mean. So here it is again. Speed has no direction. So all scalars have no direction. Velocity does have direction. All vector quantities have direction. Even further, what does that mean? Here are some examples. If you were to read or be told that a person walks 4 meters per second, that's just speed. There's no direction given. But if we said a person walks 2 meters per second north, that is velocity, because north is a direction. Again, a velocity towards Dallas, that's a direction. It doesn't have to be north, south, east, west. It just needs to be something telling you which direction it's going. Lacking a direction, speed. Now we have not gotten to force yet, but we have an example here, or two, I should say. A 14 Newton force pulls 30 degrees left of north. It's got a direction, vector. A boat is pulled by 53 Newton force, no direction, just scalar. So using our kind of vocabulary, there's going to be a little bit of work on the other side of this assignment. So let's check that out. Pretty easy. Where we just left off, you're going to be able to do these 2 boxes. So you're going to write S for speed or V for velocity, and S for scalar and V for vector. So if we're looking at our first example here, a bike goes 25 meters per second toward Main Street. There is a direction toward Main Street. So that's going to be velocity. A person walks 4 miles per hour. They basically gave us this example on the front side of this paper. That's just speed because it does not tell a direction. So I'm gonna let you guys finish the rest of these. I'm not gonna do like all of them, obviously, so you'll have some work to do to practice. But yeah, just make sure that you're paying attention to S and V. The V always has the direction. Velocity and vector are always going to tell you some sort of direction. And then the section here, just like we've seen on the first couple assignments, you're going to be looking at the variables, which are these letters on the left-hand side. And you're going to match it with the quantities, specifically the units on the right-hand side. So we're practicing learning that, hey, A is acceleration, and it commonly has a unit of meters per second squared. So go ahead and match those up, and you can use the previous worksheet that we did last week that had the table with like all of the variables and common units. And then finally, of course, there are some word problems where you're going to be using the formula. So we have 3 acceleration formulas, or 3 acceleration problems, I should say, not formulas. This one, and this one. This other one right here is going to be the speed formula. So the three that are in red are acceleration. And I am going to get you started on a couple of them. I'm going to give you a little bit more of like a hint on this one down here because it's a little bit more difficult. But these two, pretty similar. So essentially, you're going to read through the word problem just like we have been. And you're going to make your little list right here of variables. The formula that you're going to use is the formula from the front side of the worksheet, which is what we're like newly learning today. Same thing for this one. So I'm going to go through here and say, okay, my acceleration, unknown. What's my beginning speed? What's my ending speed? What's the amount of time covered? Think about that for a second. A person starts running from 2 meters per second to 6 meters per second in 2 seconds. Calculate the person's acceleration. Again, time is usually like the easiest one. Kind of look at that. And then hopefully you were able to see that beginning speed was 2 meters per second and then ending speed was 6 meters per second. So then you're going to take your formula and say A equals something minus something divided by 2 seconds. So I want you guys to fill those in correctly. And then really the same exact thing over here. This one's a little tricky because it's got the word stops. So you've got to decide, is this or this the beginning or the ending speed? Fill them in here. Solve for the equation. Okay, so take as much time as you need. Like I said, pause, come back to that if you need to. And yeah, let's go ahead and do this one, this last acceleration one, and then we'll look at some of the speed stuff. This one's a little tricky because you do have to solve for something other than A. So we have a dragster, one of those like race cars. Its top acceleration is 60 meters per second squared. So first of all, they told us the acceleration, which we haven't done yet. If it accelerates for 3 seconds, there's the time. From the starting line, how fast will it be going? So they told us the acceleration. They told us the amount of time. We need to know what's the beginning speed and the ending speed. They really didn't tell us any other numbers. So we got these two, the 3 seconds and the 60 meters per second squared. But they did ask how fast will it be going? That is our ending speed. So our S2 is our unknown. So you might be thinking, or you might already have the answer, what the heck is my beginning speed? You got to read this little part right here. From the starting line. So what would be the speed at the starting line? 0 meters per second. So again, one of those hidden zeros. So that's kind of the first tricky part. The other part is that now I do know starting speed. I do know my t, my time, and I do know my acceleration, but my unknown is not isolated. I didn't solve for it yet. So if you guys remember, we did the 2 different methods yesterday of how to do this. I'm going to show the one on here, or at least get it started, of the one that the method that everybody seemed like they kind of liked better. So if I take this formula format, and instead of saying A, I say, okay, an acceleration of 60 meters per second squared is equal to speed 2 minus speed 1. Well, I don't know speed 2, so I have to just leave it as a variable. But I do know that speed 1 is 0 meters per second, and I know that time is 3 seconds. You are now going to solve for S2. So it's going to involve moving these 2 things, the 0 meters per second and the 3 seconds. So I'm going to leave it there. I think you guys will be able to figure that out. And then lastly, oops, I almost went the wrong way. We have a speed question here. So we don't really need to write the variables this time because we're going to be using a data table. So basically, you're going to do the exact same thing that they did on the front of the worksheet here. You're going to look at the total distance compared to the total amount of time. You're going to get a number right here and a number right here, and you are going to do speed is equal to distance divided by time. So you'll plug those in. That one's pretty easy. And finally, a little bit more graphing. All right, so this is what I was talking about in class on Monday when I was like, read the titles, read all the things. You'll notice that right here, this says speed. And yesterday, it always said distance or position. So this is the change. This is a speed versus time graph. It is not a distance versus time graph or a position versus time graph. Still time down here. And it's measured in seconds. So we can see that like, okay, time is passing from 0 seconds all the way up to 12 seconds. And then speed is going from 0 all the way up to 70 meters per second. Still, it looks like a graph. It's a straight line. I can choose 2 points on it to find the slope. So they ask us to find the acceleration for the above graph. To do that, you're going to use slope. Still the same exact formula, y2 minus y1 divided by x2 minus x1. I chose these 2 pink points right here. There really are not any other good points on this line because like we talked about yesterday, I don't really want to choose that point. No, none of them really cross at a place on the graph where we can see exactly what the number is. So you'll have 0, 0, and this point right here, 10, 60. And remember that this is the y-axis and this is the x-axis. So you'll have a y2 and a y1 and an x2 and an x1 that you'll do the math right there. And then lastly, we've got a graph that has some more steep and more gradual lines, also like we saw yesterday. And they mean some different things. So they want us to look and choose A, B, C, or D for each line segment. Which one is a constant speed? First of all, we need to know that speed is our y-axis. So part A right here is a flat line, C is a flat line, B is a line that's trending downward, and D is a line that's trending like upward. So a constant speed is going to mean no change in speed, like cruise control. I want you guys to look at that and think about it. We'll check in on Thursday after you guys have done this, obviously. So constant speed, I'll give you a hint. There are 2 letters. There are 2 answers for that one. Deceleration would be the letter, and there's only one answer for this, where the speed is slowing down. Decelerating means going from a higher speed or velocity to a lower speed or velocity. And then acceleration means the opposite of deceleration. The object is speeding up. It's going from a lower speed to a higher speed. So make your choices there. And then lastly, we're going to read these 2 sentences and they're very similar. The slope of a position versus time graph compared to the slope of a speed versus time graph. There is a difference. This is the one that we did yesterday. The slope of a position versus time graph means speed, or tells you speed is maybe a more useful way to think about that sentence. And then the slope of a speed versus time graph is this, speed versus time, speed versus time. When I solve for the slope of this line, I didn't find speed, I found acceleration. So that's where they look very similar. And honestly, if you didn't read the y-axis, you wouldn't know the difference and you wouldn't even realize probably what you were solving for. It's still the same process. It's still the slope formula. It just gives you a slightly different meaning to the answer. Okay, so that's the main assignment for the day. And then I also want to go in, like I said, and add a little bit more to our, well, that's not what I wanted, note sheet. So I did this top part yesterday. If you didn't, you can pause this and fill that in. So now we're gonna look at acceleration. Try not to scroll too far down there. So we have our original like formula here. A equals delta S divided by delta T. It could also say A equals delta V divided by delta T. And remember that delta S is change in speed, which is speed 2 minus speed 1. We also could rearrange this formula if we needed to solve for change in speed. That would be A multiplied by delta T. Or if we needed to solve for the amount of time over which this happened, that would be change in speed divided by acceleration. And then I went ahead and put some common units here again, just like we talked about for the speed formula yesterday. Most commonly, acceleration is measured in meters per second squared. I would say equally common are the next two, miles per hour squared and kilometers per hour squared. But remember, you could also have kilometers per minute squared, mile per second squared. Like you could have some really weird units. They're not super common, but they could exist. So these three in yellow are just the ones that you're most likely to see. And you only know what the unit is based on the information you're given, generally speed. If you're given a story problem or a graph that's measured in meters per second, your acceleration is going to be meters per second squared. If your speed is measured in miles per hour squared or miles per hour, your acceleration is going to be miles per hour squared. All right, and then we're going to skip some of this force gravity. We will obviously come back to it, but we're going to do one more thing with the graphing. So we did this one yesterday. The slope of a position or distance versus time graph will tell you the speed. We drew a little example. And now, very similarly, the slope of a speed versus time graph will tell you acceleration. And this is a really ugly drawing. I'm just realizing now. You guys can probably do a better job of me, but draw a little graph for yourself so you very explicitly know this part. The speed on the y-axis means that you can solve for acceleration. Still, you're doing the slope formula, which is, we wrote it up above yesterday. You can rewrite it again if you want to. You don't have to. So like I said, you'll be filling out this note sheet for really the entire class, and you'll be able to use it at the end on your midterm and in the meantime on your assignments and any quizzes that we might have. Yeah, we don't need anything else there. Okay, cool. So those are the two things for today. Tomorrow we'll actually be doing a review and getting ready for a quiz, so you can see those things upcoming. If you would like to, you can view them. Of course, we'll be talking about this acceleration assignment when I'm back to make sure that I answer any questions that you guys might have, and yeah, get ready for the review and the quiz this week. If you do have any questions, you can comment on here on these like assignments, or you can send me an email. I will be posting this on the stream actually over here. And I'll put my school phone number too, so you guys can like text me if you get like totally stuck tomorrow, or anytime if you need to. I don't know if I've given that ever to everybody yet. All right, that is it, and I will see you guys on Wednesday.